In previous lectures, our focus was SAR instruments and SAR data. We're now going to move our focus onto interferometric SAR, or InSAR, which is a set of techniques that we apply to SAR data. After an introduction to InSAR and a look at different contributions to the phase signal, I'm going to move on to how individual interferograms are processed to reveal ground displacement, and then look at how networks of interferograms can be leveraged to further improve our ground displacement estimates. The history of InSAR is mostly fairly recent, but I think there should be an honourable mention to Albert Michelson, who in 1887 discovered interferometry. When coherent light sources are combined, they form an interference pattern based on how the peaks and troughs of the two waves interact with each other. Later on, people like Thomas Young realized that interference patterns provided a means of measurement. Modern satellite InSAR got its first big wow moment with the Landers earthquake in California in April 1992. The European remote sensing satellite ERS-1 was the first of its kind and designed to provide data for all, and had been in orbit for under a year when it got its first real test. Some luck was involved. We happened to get good data before and after the event, which was certainly not a given back then. It seemed likely that earthquake monitoring was a good application for InSAR, but this was the first time we'd seen InSAR capture one, and it really made scientists sit up and notice InSAR for the first time. In 1999, an Italian researcher named Alessandro Ferretti came up with the concept of permanent scatterers as a means of selecting and processing the best targets in a set of images. This revolutionized what we now call multi-temporal InSAR, or network InSAR. Prior to that, people weren't really doing much with large groups of images because large groups of images were still pretty rare. By the 2000s, commercial InSAR had got a foothold, and the oil and gas sector were an early adopter, and a handful of companies really focused on providing InSAR as a service. It was shaking off its academic roots and becoming operational, and reached commercial maturity in around 2010. By about 2014, adoption in the mining community was gaining traction, and since then it's become an entirely routine part of monitoring for many mines around the world. Recall this slide from an earlier lecture. I described the fundamental aspects of the signal, such as amplitude, wavelength, and phase. Phase is an angular measurement of length. It captures the fractional wave returned to the sensor after the signal's long round trip to Earth and back. We have no knowledge of the millions of waves that preceded it, so being a fraction of a whole wave, the phase value for each pixel therefore lies between 0 and 360 degrees, or 0 to 2 pi radians. Note the Greek letter phi used to denote phase, which is a standard convention. Also recall that the phase appears random for a single image, but actually it's highly correlated over time, as long as there's not too much time between the images and a few other conditions hold true. When we difference the two phase images, the randomness disappears. The phase difference image is called an interferogram, and this is the fundamental observable for InSAR. Interferograms formed using two SAR images separated in time. These phase differences encapsulate changes that have occurred between the two image dates, including any ground displacement. There are other unwanted effects that also shift the phase values, and the main goal and challenge of InSAR processing is to isolate displacement from these other effects. So here's what's happening to our waves. For some given pixel, On pass 1, the leftover fractional wave here is 180 degrees long. A few days later, for pass 2, the SAR takes another image from the same viewpoint, but in the intervening period, the ground has displaced a little, so now my phase is longer at 270 degrees. When I take the difference, I get 90 degrees for the corresponding pixel in my interferogram. Another way to view this is to also consider the spatial aspect of InSAR. In this scenario, area A records a phase difference of 0 degrees because the ground was stable between pass 1 and pass 2. Area B, on the other hand, has undergone some ground displacement and a non-zero phase difference is recorded. As we'll see in later slides, this spatial aspect is important. We determine the displacement at B by analysing the phase difference at B, but also we have to tie it to somewhere stable to correctly reference the displacement. We're now going to look at some other factors that can shift these phase values. Before we get to that though, let's firstly consider our InSAR geometry. This is a diagram of the InSAR geometry, in this case for TerraSAR X. An image is acquired on pass 1. 11 days later, the satellite returns and acquires another image. In general, the satellite travels on a smooth, predictable path through space, but it's perturbed by the Earth's gravity field and other celestial bodies, so it slowly drifts off course. To keep it in check, it's periodically maneuvered to stay within an agreed orbital tube, around a few hundred meters wide, to ensure it doesn't drift too far. But for any pass over some area, the satellite positions will vary. So for any interferogram, we can draw a triangle similar to this one. The triangle in reality is extremely thin because the distance between the satellite positions is a few hundred meters maximum, and the distance to the ground is around 500,000 meters. The red line shown in the diagram is particularly important, and this is the perpendicular baseline, or B-perp, as I shall refer to it, which represents the distance between the satellite positions that is perpendicular to the look direction. B-perp will vary from interferogram to interferogram. One of the unwanted effects in InSAR, for us at least, is phase effects due to topography. InSAR is sensitive to topography, the hills and valleys on the ground. In fact, making elevation models is a valid application for InSAR. But for us, measuring ground displacement, it's a nuisance. The B-perp for any given interferogram is like the eye base for this effect. The wider apart someone's eyes are, the more depth sensitivity they have. If someone's eyes were no distance apart, this would be the same as having one eye, and they would have no depth perception at all. Similarly with SAR, if B-perp were 0, there would be no sensitivity to topography. This 0 baseline would be great for those of us trying to measure displacement, because we don't care about topography. We just want to compare the lengths of two waves. So the topographic effect scales as B-perp grows. Let's watch an animation now of the effect of B-perp. In the top image are two superimposed SAR flight paths, indicating for now a B-perp of 0 meters. The SAR is imaging a mountain on the ground. The mountain isn't displacing, so all we see right now in the bottom image is a bit of noise caused by layover. As I click through the animation, the orbit paths are going to diverge and we will see the response in the phase in the bottom section. So now hopefully you can see that the paths have moved slightly apart, and in the bottom image I see some color change. This is one complete colour cycle, or fringe as we call it, going from dark blue, which is 0 phase, through green, yellow, red and back to blue. This is analogous to a height contour on a map. So as I continue to move the orbit paths further apart, I see more and more fringes for the same mountain. There is no displacement here. All of this is purely due to the increase in BPERP. The depth perception of the system is increasing because its eyes are getting wider apart. Here now are some of the main contributions to the phase that must be considered in order to reveal ground displacement. Let's take them one at a time. In later slides, we're going to see examples of all of these. Firstly, in the top left, a straightforward issue called the flat Earth correction. This is simply a phase response generated as the sensor sweeps from near range, that's pixels closest to the sensor, to far range, pixels furthest away from the sensor along the swath. This is effectively a simple ramp. We've talked about topography in the top right in previous slides. Another way to understand this is to look at the top right figure. Imagine first that there is no mountain present. The two paths are a certain length. But when the mountain is there, they change length, obviously because the mountain is higher. But what really matters is they change length by different amounts. And this difference, I hope you can see, is governed by BPERP. In the bottom left is atmosphere. Microwaves travel at the speed of light in a vacuum, but they are delayed in a medium, such as the atmosphere. On pass 1, the signal passes through a column of atmosphere with some distribution of water vapor, pressure, and temperature. 11 days later, or even after a few hours, this has completely changed. What we end up in our interferograms is a kind of clumpy distribution of artifacts based on the difference between the two atmospheric states at the two acquisition times. This is particularly noticeable, for instance, in Arizona in September, where the atmosphere is at its most turbulent during that time of year. Finally, in the bottom right, we have displacement. This is a straightforward increase in one of the path lengths because the ground got a little further away. Always remember that we're not differencing the entire path, just the leftover fractional wave that the satellite records.